So the aim of this video is to give you the opportunity to practice and gain feedback on your mastery of the method of sections. So here is a truss. Information about the truss is written here with supports. This one is a roller support, and there is a load here, vertically downwards. And the question asks you to use the method of sections to find the following tensions. So what I suggest you do is attempt to solve the problem, and then afterwards come back and you can see on the next slide whether you've got the answers right or not, and then I'm going to give you a detailed solution. And I hope this will be helpful to you. So see you in a while after you have tried to do the question. That's the way to really gain benefit from this. Okay, welcome back. Let's look at the answers. So here are the answers for the three tensions. They are given exactly, which is possible to do because the angles in the triangle are 60 degrees. And they are also given to two significant figures. You can see that one of the tensions is negative, and that means that that particular member is in compression. And if you've got the correct answers, congratulations. And what I'm going to do over the next few slides is go through a solution. So the first thing that I've done here is I've just copied and pasted the diagram. I've been quite clear about the angles, and I have marked that the distances along the sides are 6 meters, and the three members whose tensions we want to calculate I've shaded in white. I've also added here the reactions at the two supports. This is a roller support, so we know that any reaction is going to be straight up or straight down, and this is the reaction here. So firstly, we look for global equilibrium. We look to see whether the sum of the forces adds to 0 in various directions. So horizontally, this load has 0 horizontal component. This is vertical, so this is the only force in the horizontal direction. It must therefore be 0. Vertically, we have the sum of R1 and R2 must be equal to the compensating downwards load of 12 kilonewtons. So we have this equation here. And then we can calculate the moment about a point, and I've chosen to take moments about A. You could take moments about here, or you could take moments about here. But let's take them about A. And the load is generating a clockwise moment about A. So it has a negative contribution of minus 12 kilonewtons multiplied by this distance. Now that's 6 meters. That's 6 meters. This is bisecting the triangle, so this distance would be 3 meters. So the total distance from here to here is 6 plus 6 plus 3. And that is the perpendicular distance from the point that we're taking moments about to the line of action of this force. The only other force is R2. This is acting in this direction, which would generate a positive moment, and the perpendicular distance is 6 plus 6 plus 6, so 3 6s, and the force is R2. The sum of these two moments must be 0. We can solve for R2 by taking this term over to here, which will make it positive, so we'll get 12 times 15, 6 plus 6 plus 3 is 15, and then we divide by this number here, and that's 3 6s, which is 18, so we divide by 18. 12 over 18 is 2/3, 3 goes into 15 gives you 5, so we have 2 times 5, that's 10 kilonewtons. So our force, R2, is 10 kilonewtons, and then we go back to this equation, and we say, well, if R2 is 10 kilonewtons, this is 12, R1 is going to be 12 minus 10, so it will be 2 kilonewtons. And if we just think about it for a second, that makes sense. This load is almost above that. I would expect this to compensate that. So I'd expect R2 to be relatively large, and I would expect R1, some distance away, to be much smaller. And that's exactly what we have obtained. Okay, so now we know what the reactions are, and we can take a cut through here, and we will be able to calculate the forces in these three members. So let's go to the next slide. So on the first slide, I've drawn the truss again, and what I've done here is I've just shaded in white the three members whose tensions we want to calculate. And I've written out here explicitly that the length of the members is 6 meters, and I've also shown that the angles are all going to be 60 degrees. First of all, we use the idea of global equilibrium. So horizontal forces have to add to 0. This is a roller support, so the only horizontal force could be here, since the load is vertical. That tells us that this is 0. The vertical forces also have to sum to 0, so R1 plus R2 have to be equal and opposite to the load. So R1 plus R2 is 12 kilonewtons. And now what we do is we take moments about a point over this extended object to obtain a relation which will give us one of the reactions. And I've chosen to take moments about point A because that does not include R1, but it will have a contribution from the load and from R2. So what are the vertical distances of these forces? Well, the load is vertically downwards. It acts through here, through the middle of this triangle. So this distance is 6 meters, this is 6 meters, and this is 3 meters. The moment here is going to be clockwise, so it will be a negative moment. So it's going to be minus 12, that's the size of the force, times this distance, 6 plus 3, or 15 meters. For R2, it's an anti-clockwise moment, so it's positive, and the distance is 6 plus 6 plus 6, so 18 meters. We have this equation, rearrange it, and we obtain that R2 is 10 kilonewtons. From this equation, that tells us that R1 is 2 kilonewtons. Does that make sense? Well, the load and R2 are acting close together, so it is fairly logical, I would say, that this load and this load are going to be similar in size, and this force, this reaction force, which is much further away, is going to be smaller. So yes, that seems plausible. Okay, we can now use these values and the method of sections to find the tensions in these three members. Let's look at the next slide. So on this slide, I've drawn the picture again, and I've explicitly made the cut that I referred to in the previous slide. And we can now consider either this side of the cut, or we can consider this side. And the method that we use to make that choice is a very simple one. We choose what looks to be the simpler side. And I would say this looks simpler than that. So let's consider this here. And all I've done here is I've drawn this again. So now let's think about it. We have the load up here that or the reaction rather up here that we know. We have the load here, and we have the tensions in these three members that we're calling TCD, TCF or TFC, and TEF here. And because the letter C is in both of these names, you can see, no pun intended, that the lines of action of these two forces along the members are going to meet at that point. So that can be very useful for taking moments. So now that we are, I hope, happy with this diagram, what I'm going to do, just to give myself more room, is I've just copied it, and I will put this diagram at the top of the next slide. So here is the cut that we're going to make through the middle. It's cutting 3 members. Remember, in the method of sections, we don't cut more than 3 members. And we could either now examine this or we could examine this. And the basic idea is we choose the simpler looking half. So we're going to examine this. I'll draw it again, or copy and paste it to be honest, on the next slide. So this is what we're going to examine. Here are the 3 tensions that we want to calculate, and I've extended their lines of action so that we see that they join at a point, which is also clear from their names, TCD and TCF or FC. They're joining here. So that's going to be useful in a moment. We're going to need a bit of geometry. So our triangles have all got 60 degrees as the angles. It's an equilateral triangle. And if you have an equilateral triangle, you can drop a perpendicular. And then if you say that this side is, say, 2 meters long, and that's 1 meter long, from Pythagoras' theorem, this would be the square root of 3 meters long. And we can work out all of the trigonometric functions for 60 degrees and equivalently 30 degrees as well in that way. What we're going to use here is that the tangent of 60 degrees is the square root of 3 over 1. It's root 3. So the height of this triangle is going to be this side. This side is 3 meters. This divided by 3 meters is the tangent of 60. Rearrange that. The height is 3 meters times the tangent of 60. We know the tangent of 60 is root 3, so the height of our triangle is 3 root 3. And that's somewhere between 4.5 to 5 meters roughly. We're now going to take moments about point C because it gets rid of 2 of our unknowns. So we have 3 contributions, a moment from the force TEF, a moment from this known load, and a moment from this known reaction. So from the load, we have a force acting vertically downwards. This distance here is the perpendicular distance from the point C to its line of action, and we know that that is 6 meters. So we have a clockwise or negative moment of size minus 12 kilonewtons times 6 meters. We also have from the reaction force, which we've calculated to be 10 kilonewtons on the previous slide, a positive moment, so it's plus 10 times this distance, which is 6 plus half the distance of the side of one of the triangles, or if you wish, you can view it as that distance plus that half. Either way, it is 6 plus 3, or 9 meters. Then from TEF, we get again a negative or clockwise moment, and its perpendicular distance is the height of the triangle, and that's what we calculated a few moments ago. So we get minus TEF times the distance 3 root 3 meters. The sum of these moments is 0. So if we take this to this side, it's positive. We take the other 2 then, we have plus 90 from here, minus 12 times 6 is 72. So we have TEF times 3 root 3 meters is 18 kilonewton meters. Dividing both sides by 3 root 3, we obtain 6 over root 3, 18 over 3. And then we just multiply here top and bottom by root 3. So we get 6 root 3 over 3, which is 2 root 3. And the meters have cancelled and the units are kilonewtons. So we've calculated the first of our tensions, and we see that this is in tension. On the next slide, we'll look at the others that we still have to obtain. So if we look at the two unknown forces, here and here, what we see is that this is horizontal and this has a horizontal component, but this also has a vertical component. So if we say that the sum of the forces vertically has to vanish, then we can work out what the force is here by saying that its vertical component is TFC times the sine of this angle, sine of 60, and then it's minus 12 downwards and plus 10 upwards. So TFC times the sine of 60, which is root 3 over 2, is going to be equal to, well, this is minus 2, take it to the other side, plus 2. So TFC is 2 times 2, 4 over root 3, which is 4 root 3 over 3 kilonewtons. And again, we're getting a positive answer, so this is in tension. And on the final slide, I want to look at the forces horizontally, and we now know what the horizontal component of this is going to be, because we know its magnitude and we can use a little bit of geometry. And only this and this is horizontal component are going to have to cancel that. So we can see immediately, without doing the calculation, that because these three horizontal components sum to 0, TCD is going to be negative. This member is going to be in compression. So here is our diagram again. I've written out the values of the forces, and horizontal forces are 2 root 3 kilonewtons from here, 4 root 3 over 3 kilonewtons in this direction times the cosine of that angle, the cosine of 60. The cosine of 60 is just a half, plus TCD. So TCD is going to be equal to, we take this over to here, this over to here, so both contributions will be negative, so minus sign, open brackets, add these two together, 2 root 3 plus 4 root 3 over 3 times a half. So let's take out the 2 root 3 common factor from here, and 4 over 2 is 2 root 3. So we have 1 of it plus a third of it, so that's 4 thirds. So we have overall minus 2 fours are 8, root 3 over 3 kilonewtons. And I'll just add the units here. And because it's negative, we see that this is in compression. So previously, at the very beginning, I put the answers to two significant figures, and I hope that this video has helped you. Okay, with that, I'll stop.